first slides, there's data-driven positioning. Why? These machine learning approaches need a lot of data. I briefly said already at the screen in the demonstration. In our case, the data are channel impulse responses, for example, together with labels that we need for training, so reference positions. Here in our test bed, of course, we have reference systems. We have multiple reference systems, laser-based, optical-based, with cameras and so on. So this is an environment, of course, where we easily can get labels. During the presentation, I will show you how we can a bit get rid of the labeling and be more flexible, and have more automatization later on when you do the positioning in your use cases on premise. So let's have a look at the next slide. So this slide briefly introduces again what happens. So you see on the right side our environment here with some obstacles that we placed, also the shelves. And you see the signal propagation here sketched with green, the direct path, which is blocked by the shelves, for example. In yellow, a scattered path, and in orange, a path with reflection at this wall that we can move around. And you see next to it, the channel impulse responses, also as a sketch. So in green, it's the one if you have a direct line of sight path, so you have a clear maximum, and it's quite easy to detect the line of sight path and to do, for example, uplink TDA-based position. But if you have the blockage and the reflection, then it's much more hard to tell where is, in this case, the time of flight. Yeah, if you go for maximum, you would go, for example, for this peak here, which can be wrong in this case. Yeah, so the distance estimation is erroneous if you have blockage, reflection, and scattering. But the channel impulse response contains the spatial information that you can use to improve your positioning results. When we now come to the AI-assisted localization, we distinguish here between a direct and hybrid positioning. So the direct positioning is also what we saw here in the demo case a few minutes ago. That is, we collect channel impulse responses, and in this case, time of flight information too. We train a neural network with it, and then we use the neural network for the positioning. So direct, because you directly use the neural network from input to output to get a position. Yeah? Hybrid positioning, on the other hand, there we estimate the channel conditions. What does this mean? This means, for example, in the easiest way, that you like to distinguish, do I have a line of sight path? Because if I have a line of sight path, so for example, in a very free area where there's no machinery and nothing around, you can do uplink TDA-based positioning, and it is maybe the best that you can do there, together with maybe some filtering afterwards. But if you have a non-line of sight case, so blockage of signals and then reflections and scattering and so on, you like to know that, because in this case you can adapt your filters, or you just can, for example, put away some time of flight measurements where you see that they are blocked signals. So these are the two approaches that you can do, and there are much more, but these are the simplest ones to understand how AI can help. So you can use it to directly calculate the position, or to assist the traditional positioning approach, like with uplink TDA and the base filter, for example, in the end. Then let's have a look at the channel impulse responses in more detail. Here in this example that you see, we had a measurement campaign also between the shelves, moving around here in circles, and you see here the one channel impulse response. If you have a clear peak, you have a line of sight. Here in this case, we look for the station 2. So here we had line of sight. Now there is some blockage by the forklift here, and we come here in an area where we have a clear line of sight again. Yeah, and you see here that for this example, we had six space stations in this case, or 6 antennas around that we used. And we used the whole channel impulse response here for the direct positioning to using a convolutional neural network, in our case, to calculate the position that you saw in the demonstration. So in this way, we somehow interpolate the fingerprints with the convolutional neural network because we have collected a lot of data in the area, which are the fingerprints. So one typical channel impulse response for each signal received for each point. And the neural network helps us to later have less memory that we need to do the positioning. Yeah. So this video was a bit for if something's not working. But let's have a quick look inside. So this was a recording of the 5G Connect. Maybe you were there, that we had where we the first time presented the positioning here in the link call, just with the mobile robot. Today you saw it also with a smartphone in hand and and we could walk around as we want. What we see here, and this is why I show it, we see also the accuracy, which is important. Here behind the shelves, we saw that the orange position, which is uplink TDOA, the error is higher than 1 meter. 1 meter is this line here. Maybe you cannot see it on your screen. This is the 1 meter. We want to stay, of course, below 1 meter or even much better. In the open space, both work quite well. Yeah? So you have a very high accuracy or a very low positioning error in this area. But if we go behind the shelves, maybe I stop it here, then we have the scattering and the reflections and the blockage of the direct line of sight, for example, from all antennas which are here or to all antennas which are here around. And the uplink TDOA positioning starts to have a higher error than the machine learning based approach. Yeah. In the video, we see now the robot coming again in the area where we have good line of sight to all of our antennas. So the positions of all are quite well. Yeah. Here you see some correlation input. This is similar to the channel pulse response that we saw before already. Now, how can we improve to get rid of the labels? Because that's one big part that I said. And how can we achieve the maintenance of our models that we use for positioning? This is here in the life cycle management demonstrated. So first point is uncertainty estimation. Uncertainty estimation means that we take the measured signals and we have a look if the measured signals fit to our model that we have trained, so fit to our model so that we have a very high accuracy. Because if there are big changes in the environment, like you see here in red, our van moved from one spot to another and there came another object inside, and we have here a red area, so a high uncertainty. That means our model does not fit in this area to our measurements, and we can detect that during the measurement process, so during the positioning. So we can indicate, I'm sorry, but my positioning accuracy is at the moment not very high, and we need more data in these areas to be able to have a high accuracy again. For this, we use, for example, transfer learning to repair the corrupted model that we have trained already, and to maintain our model then in the process. So this is the first part. And now let's get rid of the labels. And for this, we use unsupervised fingerprinting. Maybe I say a few words on supervised, unsupervised fingerprinting. So supervised fingerprinting means in this case, for example, that we have the labels available. So we have the truth available, the information about the truth, and we give this into our training to get the model. Here we have an unsupervised fingerprinting. We don't have labels, or we only have a few labels in place that we use in addition, but we exploit our radio signals in a way that we get the geometry of the data. That means you do measurements at certain points here in the link call, for example, and from the channel impulse responses, you can estimate the distance in space between these measurements. And using these distances from all measurement points, you can get again a representation of your environment in your models. that you see here in these examples. So on the left side, this were the true tracks, and on the right side, this was the result from the trained model with channel charting. Of course, we see, okay, here it's not totally the same, but if you add then very few reference positions inside, it gets fast much better. So this is what you see here in the graph. You have the 90% positioning error here on this side, and you have the number of label training data that you need to get a high accurate position. So like, for example, in the range of 1 meter. And you see that with the supervised fingerprinting, which was our direct positioning that we showed, you need a lot of labels. Yeah. And with the unsupervised channel charting approach, already with a few labels, with just a few reference positions that maybe you have in the beginning, you can already train a model that works very well. The accuracy is a bit worse still, but this is a part we are working on. Yeah. Yeah, I just show a bit the history because today it's the 10th, but we are working on machine learning in positioning and in 5G now since a lot of years. And of course, we wrote a lot of papers. If you're interested in some parts, in some research topics that I showed in the slides, then please contact me and I can forward you the papers. In the end, now let's have a look at 2 application projects. The first application project started just before Christmas. We were there in Bischheim in France at SNCF, so the rail company of France. And there they have a big facility with lots of holes where they refresh the trains. So they put everything out of the trains after like 15 years, 20 years, and they get new furniture, new cables and everything inside. And they like to track, of course, the wagons, but also forklifts and different assets there in this area. And we started a project now with SNCF, Nokia France, and University of Lorraine, that's Gran. And from Germany, the company that manufactures the robot that we saw also here, Cortex. And we are now developing algorithms to be able to do a high accurate positioning in their environment with all these big metal parts around that are also moving. And we are developing a mobile 5G positioning testbed. That's the part of Max that we saw, to be installed on premise together with the Nokia 5G campus network there. And then we like to demonstrate that we can have this high accuracy in such a harsh environment and learn from it a lot, of course, to improve our algorithms and our methods further, to be able to also, of course, bring positioning, 5G positioning in your companies on the premises and get it working and maybe comparable to other systems that are there already, or even better, let's see. That's kind of a discussion. And with this slide, sorry, I forgot the last application project. Karin already mentioned it. So it's the 5G Rettungsbürger. You maybe already know it because in 5G Dialog before, I told about a lot of details of it. Here, I just want to mention that in the 5G Rettungsbürger project, for example, we do a hybrid positioning. So hybrid positioning, in this case, hybrid systems. So we have in GNSS, so Galileo GPS outdoors that you can use for positioning, or that is used for positioning, of course. And we combine it with 5G positioning. You can combine it, of course, with other positioning techniques too. So indoors, there are a lot available. Outdoors, there are much less. Only GPS Galileo at the moment, some LTE, but not very precise. But with 5G, we think, and we are doing our research on that topic, that you can, for example, much more precisely do the localization of drones outdoors, because all the satellites are in the sky, but the 5G network is on the ground, and this gives you a much better, it's so-called illusion of precision, because you have also signals from the downside, and you can improve the positioning. And also you have the case that GNSS is blocked in urban areas quite often, or if you're close to some houses and so on. So this is what we're doing in the 5G Rettungsbürger project, and you can have a look, of course, on the project website to see what else, because it's just one part of this big project which is done to improve the processes there for the firemen. So, okay, but that was the last slide from data-driven positioning. Thanks a lot, and now let's see what are your questions.